This is an introduction for an instructional video series designed for experienced on-highway truck and off-highway equipment technicians on the practical use of an oscilloscope to diagnose various types of problems. Most of the examples that I'll use will be taken from real problems on John Deere machines, but the concepts will carry over to other equipment manufacturers. So my experience spans almost 50 years working first as an auto and truck mechanic, and then as a technician, and then as an electrical engineer in the automotive industry. My former employers as an engineer include International Truck and Engine, which is also known as Navistar, and John Deere Power Systems, from which I am now retired. So much of my engineering experience has centered around diesel engine diagnostics and controller area networks, or CAN. Specifically J1939, which is the heavy-duty on-highway truck and off-highway equipment CAN protocol. In this series, I'll be using a Picoscope automotive oscilloscope model 4425 like this one. This is a very easy to use, compact, PC-based USB 4-channel oscilloscope in this case, designed specifically for automotive technicians. Being a PC-based oscilloscope, you can use the laptop you probably already have as the scope display. Pico has some really good training material on their website, which I have linked in the comments, so I will not be covering much of the fundamentals of oscilloscopes, more how to use the data to diagnose problems on commercial vehicles. One of the great things about Pico is that anyone can download and install their automotive scope software for free without having to own the oscilloscope hardware. This lets you operate in a demo mode, and you can open data files that other users have saved. I will also be using an electrical circuit simulation program called Circuit Lab that I show here to illustrate some of the key concepts. Circuit Lab is mostly used by engineers and electronics students, but I found that it makes a great tool for teaching electrical concepts. I myself use Circuit Lab regularly to model the circuit when I can't understand why I'm seeing something that doesn't make sense on the oscilloscope. So with Circuit Lab, I can build a virtual simple circuit like this one and drop in voltmeters and ammeters to predict what I would see on a real circuit. So when I close this switch, close this, goes from open to closed. And when I close the switch, I can see that I have 6 milliamps of current that flows as predicted by Ohm's law. I can see that the 12 volts from the battery also divides equally among the two 1000 ohm resistors. I can also change one of the resistors. In this case, we'll go from 1K to 100 ohm, and we'll see that the voltage that is dropped across this 100 ohm resistor is now 1/10 of the voltage that is dropped across the 1K ohm resistor as predicted by Ohm's law. And as we can see, as we expect, the current increases from 6 milliamps to 10.91 milliamps in this case. I can also model what will happen in the time domain, which is what we're going to see on the oscilloscope. In this case, when the switch closes, the capacitor is going to be charged by the battery. The amount of time that it takes for the capacitor to charge is going to be a function of this series resistor. So if we watch if we simulate this in time domain, we'll see here that the voltage across the capacitor increased from 0 volts up to almost 12 volts in a period of time of about 5 thousandths of a second. Here we see the current that is flowing through the circuit, through the resistor in the circuit. We'll see that the current goes from 12 milliamps down to almost 0. So if I were to change this resistor from 1K ohm, change it to something like 100 ohms, the capacitor is now going to charge faster because the current will be less impeded as it flows through the resistor. So let's take a look at what happens in the time domain. And sure enough, within about 500 microseconds, the voltage across the capacitor is nearly the battery voltage, and the current flow through the circuit is nearly 0 amps. So we can see that change of the resistance. If I were to try to watch this with my digital multimeter, in either case, what I'm going to see is the voltage will go from basically from 0 to 12 almost instantly. So this is one of the advantages with an oscilloscope. I can watch something that's going to happen very quickly. I can view that with respect to time. Additionally, I'll use an engineering tool called Canalizer to help explain some of the fundamentals of J1939 CAN at what I'll call a pseudo engineering level. So understanding some of these fundamentals is necessary to become proficient at using an oscilloscope to diagnose many types of CAN issues. For example, here we can see a J1939 CAN message that is being broadcast by the engine controller. I know that it's the engine controller based on its source address of being 00. So this particular message is called EEC1 and it contains engine speed information. So in this case, the engine speed is 1689.250 RPM. That information is displayed in these 2 bytes of this message. So the tachometer on the machine knows to look at this particular message, which we call a PGN, a parameter group number, from the engine controller, and it knows to look at these 2 particular bytes and knows how to scale and decode those to be able to convert that to engine RPM. So using some knowledge of the J1939 protocol to diagnose a real problem, here are the CAN waveforms from a John Deere 8R tractor, which had a very intermittent communication issue that caused a variety of problems for the customer. So with the Pico scope, I was able to capture the issue, which, as you can see here towards the end of this waveform, there's obviously a change in the pattern and the way that the pattern looked. With the Pico scope and understanding some of this knowledge of the protocol of the J1939, I was able to decode these messages and using the information provided to the technician, which shows what we call the topology of the network, or physically how the controllers are laid out next to each other, we were able to determine the source of this problem, which ended up being a very high resistance, intermittent resistance at a terminal junction within one of the wire harnesses. We were able to fix this rather quickly and get the customer back into the field. This example will actually be one of the examples that I use much later on, because there's quite a bit of detail that we have to go through first and get some of the background to be able to understand. But just briefly here, we can see this thing called the source address. And I told you previously that source address 00 was the engine controller. Here we can see that this engine controller is transmitting, or we're able to see that it's transmitting, but there's some sort of issue here, as well as several other controllers. So it's not just the engine controller. We also have this controller using a source address of 5. So we'll go into a lot of details on this particular problem. It's one that is a little more advanced, but my goal at the end of the series is you'd be able to take a waveform like this, be able to decode this, and to be able to diagnose this down to the actual one spot in the wire harness where we have an issue. So in my experience, there seems to be a lot of misinformation and misunderstanding of J1939 CAN in the service world. Because J1939 CAN issues are probably some of the most difficult problems to diagnose, this video series will have a lot of detail on J1939 CAN. And as you can see, the Pico scope has a lot of capability when it comes to diagnosing J1939 CAN issues. There are other manufacturers of oscilloscopes out there. I haven't used a lot of other ones. I'm sure there are others who have some of these capabilities. I've used Pico for a number of years myself, so and I've become accustomed to it and really like it. So I'll continue to use the Pico scope in this throughout this series. But if you have a different manufacturer scope, you'll have to investigate with that manufacturer of how to be able to maybe do some of the things that I'm going to show how to do on here, provided it has that capability. Besides J1939 CAN issues, I've used oscilloscopes many times to diagnose diesel engine performance issues such as cam and crank position sensor issues. So with an oscilloscope, we can determine the relationship of the cam and crank signals and compare those to a known good engine to see if there's a timing issue, a problem with the target, or some outside electrical noise is making its way into the signal. So in this example that's taken from a John Deere level 33 9-liter engine, which is a 6-cylinder, we can see that the cam position sensor output in red and the crank position sensor output is in blue. I didn't acquire this data myself, but rather I downloaded it from Pico. Pico has a collection of waveforms which other technicians have taken from machines. Oftentimes, hopefully, it's a machine that does not have a problem. In this case, we can then use this as known good data if I'm working on, if I happen to be working on a 9-liter myself and I have either a cam or a crank sensor fault and I'm trying to figure out what should a normal pattern look like and I don't have another machine. So some of the really cool stuff that's here, I can even determine what the engine speed is here. So I'm going to go ahead and use this time cursor. I'll move one here. I'll take another one. I'm going to drag this other one over to this point. So as I said, the blue is the crank position sensor output. We can see the gap, the time gap that's there. So if I go from gap to the beginning of the gap to beginning of gap, I can see that I've got a difference in time that's going to equate to, because of this machine understanding that I moved from this point to this point, I've got 900 RPM, which sounds right. That's where this engine is probably idling on this machine. So go ahead and get rid of these guys. If we look at the red signal, this is really cool. So this cam position sensor on the back of the cam position sensor, so that the engine controller, ECM, or as John Deere calls it, ECU, knows when it sees the gap in the crank position, it doesn't know if it's on top dead cylinder, top dead center of number 1 or of its companion cylinder. So to determine that, there's an additional pulse on a John Deere engine on the cam position sensor that it's going to read before it comes around near that top dead center number 1. So here we can see that sync pulse, as it's called, is coming in. We can see that this is the cam position sensor. This is the crank position sensor. And I know from John Deere, what is desired is that the cam position sensor, where it zero crosses, so it crosses 0 volts at this point, it falls within that gap. And so if everything's done correctly, we would see this pattern. If the cam and crank were out of time, or we had a problem with the target, that it had moved or drifted, we would see that this gap, that this signal would be moved in time relative. So this is another great use of oscilloscope. Obviously, with your digital multimeter, you couldn't begin to do something like this. We can also see here that these are something called variable reluctance sensors, whether you realize that or not. If I look at the sensor output, I can see that I've got an AC voltage on the crank position sensor. It has many more targets and it's turning twice the speed of the camshaft, as we know. So therefore, we can see that it has a much higher amplitude of voltage. In this case, this is somewhere approaching, where we have here, about 25 volts peak, or about 50 volts peak to peak voltage. So it's a lot higher voltage coming off that miniature alternator, if you would, which is that variable reluctance sensor. So this was just meant to be an overview, just an introduction into the series. These will be the kind of details that we'll look at as we go through this series. The other thing I'll do is I'll try to use as many real-world failure examples as possible, and I'll try to limit the theory and, of course, the math to just all that's necessary to be able to diagnose the problem.